Thank you very much for the introduction. Um, this is a joint work with my advisor, Nasir Memon, with the title of Detecting Structurally Anomalous Plugins within Enterprise Network. The inspiration for this work came from the time that I was doing an internship with a financial company in Wall Street, and I was working closely with a group of security operators whose job was somehow in a room similar to this. And they had a number of monitors each, and in each of those monitors, they were monitoring the activities of the network, and they were investigating logs from network intrusion detection systems, antiviruses, and all sorts of security tools that you can imagine. They were doing a good job in maintaining those softwares and investigating the alerts, but at the same time, as you can imagine, nobody is sure that they are doing a good job with protecting their networks. So they invited a group of so-called red team to do a penetration testing process to see if they can do anything interesting in the network. So they set up a contract, and a group of skilled uh, people, hackers, basically ethical hackers, they came and they were given a desktop with a non-admin user and an email account, which they could use to communicate with the outside. And they were allowed to do whatever they can without incurring serious damage to the network or data. Um, the longest story short was that after 2 days, they were able to take over the entire network, and I mean it. So they take over the domain controller and disaster recovery center and everything, and they come up with different information that they could find within the network. And after doing this practice and showing that we actually did that, they provided a report that how they actually did this. And I was very lucky to get to read that report, and that was the inspiration for this work. The core insight from the operation of the red team was that opposite to the fact that to the um, idea that everybody thinks that the attackers, when they come to the network, they use remote vulnerabilities to move from one machine to other machine to get to the main servers. This red team, um, they stole and use stolen credentials to move laterally within between machines and get to the main server that they wanted. And basically, after I read this report, it was clear that, well, existing intrusion detection systems and antiviruses and security tools, they cannot detect this sort of attack because the red team, or as I will show, most of the attackers, they use um, username and passwords to move laterally within the network. And this was the inspiration for this work, as I said. And uh, as you can imagine, it is not only for this company. It is actually what happened in Target's data breach in 2014, where the attackers they stole credentials of Fazio, which was a service provider for Target, the company. They had a server hosted in Target's network, in which the role of this server was that it was monitoring the air conditioning and the ventilation devices that they had installed for Target. And when the attacker stole the credential from Fazio, they used the credential to log in to the server which was hosted within Target's network. And from there, they stole new credentials to pivot their attack to target servers, and from there they pushed malware to point of sales, where they could read the information of 40 million credit cards as users swipe into these devices. So as you can see, this practice is kind of common. The same thing happened with JP Morgan, Chase, and some other big data breach incidents. If I want to describe how the attackers basically they steal credentials and move laterally within the network, um, uh, we can imagine if we have this network, the attacker usually start infecting one of the machines using a spear phishing and using a zero day vulnerability to take over one machine and get admin level privileges. And in one of the cases, for example, the attacker may start slowing down this machine so to get the attention of a help desk admin. So as the help desk admin log into the infected machine, um, basically the attacker can use tools such as Mimikatz to read the areas in the memory which password is located as the help desk admin enters to the infected machine. And then after that, use the stolen credential to log in from the infected machine to other machines, including this machine, which is an admin's machine. And from there, steal new credentials to log in from admin machine to most important servers, which basically host the crown jewels or the most important data within the network. As you can see, there are two type of malicious logins. One of them which create a new edge in the graph of logins, and one of them which moves over the existing uh, edges of the graph of login. And these two type of basically malicious login, they need different approaches to detect. Uh, we started the first project basically by detecting malicious logins which create new edges in the graph of logins, and that would be the topic of this research. Okay, so one naive idea might be that we get all the logins of the past in the network for 2 months, 3 months, 4 months, for a long period of time in the past. And then whenever a new login comes to the network, we compare if we have seen this login before, we say that this is okay. If we haven't seen, then we create an alert. We basically did a data analysis on a large number of logins within the enterprise that I mentioned. So we got 4 months of previous login within the network, and we created the graph of login, and we started measuring how many logins from that day until the past month, the next month we have seen in the past. As it shows, even from the next day after we create the model, only 95% of those logins are observed in the past. And as it goes, it just start dropping. So we see new login within the network in a normal manner. It's natural that lots of new login happen within the network because of several reasons: new users, new servers, load balancers, and change in activities of the users. So basically, if you want to use this naive exact matching of logins within the network, we're gonna get lots of alerts, which basically between 8 to 20,000 alerts per day. So it's not gonna work. But we had another insight from the study of the behavior of basically attackers within the network, and that is the fact that a large number of logins, specifically in the beginning of the attack, from attackers, they are not consistent with what we call as a structure of the logins within the network. Let me give you an example of what does it mean, what does the structure of the network means, and how the attackers they may do a login which is not consistent with the structure of login. So imagine that we have a sales department, and users of the sales department use an application which is providing some way of putting information into that application for sales users. So basically, the sales users they use their own desktop to log into those servers. And at the same time, we have DB engineering people who maintain the database which belongs to that application. And as you can see, most of the users in the sales department they log in to this server. So if sometime in the future, we see a login from C4 to the application server, we're going to say that this is a normal login. Versus if we see a login from C4 to DB server, because it's not consistent with the structure of the network, we are going to say that this is a likely abnormal or malicious login. And we can describe the structure of the network using patterns, saying that the users of the sales department using their desktop, they usually log into the sales application server, and DB engineers using their engineering desktop, they log into sales DB servers. So we can define the structure of the network with these triplets and then compare the new coming login with these structures. So considering a structure of the network, we are able to detect various type of malicious logins. So if this is the normal structure of the network, if an attacker steals a credential U3 and use a computer which usually connects to a destination but using a different credential, we are going to say that this is a suspicious user. We don't expect that this user connect from S2 to D1. Another type of malicious login happens when the attacker uses stolen credential to a destination which user usually connects to, but from a malicious source computer. And it is actually what the authentication systems at the moment are not able to manage that, because they usually consider the credential but not the source of login within enterprise network. And the next type of the malicious login is the type that, well, the source of login and the user is okay, but the destination is not what we usually expect. So based on these insights, we have designed a system which is able to detect this type of structurally anomalous login. So this system has two different sections or parts. The left side, as you can see in this diagram, is the part that basically using a mining algorithm extract the normal structure of the network by extracting and mining normal login patterns. The input to this module are logins in the past for a long period of time. The other input is the attributes of users and computers, including the location of the user, HR category, type of the user, and also some attributes of the computer, which includes location, type of machine, is it a server or a desktop or a laptop, and what is the type of application which is hosting, is it an HR application or another type of application. So using these inputs, the mining algorithm extract the patterns of login and then generate these patterns. The second part of the system is the part that actually does the classification. Basically, again, we have a classifier when we get a new login. We also match that with attribute of user and computers and use the login patterns to compare and see if the login is normal or malicious. And the result would be a labeled login. Is it a normal? Is it a benign or a malicious login? The core of our system is the pattern mining algorithm. To describe how the pattern mining algorithm works, I have to first describe how we model a login. We model a login using a tree a structure which has three items, including user, which is used to log in, the source machine, which login occurs or happens from, and the destination machine, which is the destination of login. So this triplet, the ID of the user, source machine, and destination, they show a login uniquely. In another level, we can show the same login with the attribute of these components. So we can say this login is from a user which has these attributes, from the machine that has this sort of attributes, and to the destination machine, which has these sort of attributes. And as I said, example of attribute of the user would be type and business unit, and attribute of computer can be type, application name, and location. And you're free to use different type of attributes, and our algorithm is flexible to include them. So based on this representation, now I can describe how the mining algorithm works. So the input to the system um, would be the attribute level representation of logins. So L1, for example, would be an attribute representation of attribute of the user, attribute of the source, and attribute of the destination machine, which were involved in this login. So for each of the logins, we compute the Cartesian multiplication of the power set of the attributes, because we don't want to fix the attribute saying that a user with all these attributes from a computer, from all these attributes connected to a destination with all these attributes. Any combination of the subset of these attributes also can create a pattern. So as a result, for each of the attribute of the user, we create the power set of the attribute. For attribute of the source machine, we create the power set of attributes. And for destination, the same. And we multiply all these and compute the Cartesian product of these attributes. As a result, we enumerate all the candidate patterns, which can somehow define a substructure of the network or a pattern of the network. So, of course, some of these are obviously not useful. For example, the one which is the result of multiplication of all empty elements of the subsets. We can remove them basically by creating a rule. But other than that, we need a measure of confidence for each of these patterns to say that, well, how much we can rely on this pattern. And if you want to consider that, it's very similar to the concept of the confidence in the market basket analysis algorithm, where you extract some rules and then based on the ratio of the uh, example of that rule to the all possible example of that rule, then you compute the confidence. But here, the problem is a bit more complicated, and I will demonstrate using this example. Imagine that you have a rule saying that users of the rectangle department um, log in to computers of the oval department. But this can have different orientations. For example, one orientation might be that a large number of the users from the rectangle connect to only one server here, or a user from here connects to many of the servers here, or only one computer to the destination of these subsets, but many different users. So the first type we call it source oriented. Uh, so basically, if in the future, for example, we see a login from the fourth computer to the same computer in the destination, we kind of expect to see that login, and it would be normal, because in the past, in the history of the logins in the past, 3 out of 5 of the computers they connect to the destination. So as a result, for example, we compute a source score for the orientation type A, and that would be 3 over 5, which is 0.6. And these values are values between 0 and 1. And at the same time, if we compute the D score, which shows the range of the computer in the destination that we cover based on the history of the logins, we see that only one login from this type of computers were the destination of login. As a result, the confidence or orientation score for the basically destination D score would be 0 to 25. And as a result, for example, if we see in the future that a computer from the rectangle department connects to a new computer in the destination, we kind of detect that as abnormal because we don't expect to see that. Okay, so for each login, we compute three different confidence score. And then, as I said, we have a number of patterns and we extract them. Okay. So we have evaluated the performance of the algorithm based on a real data set from the same financial company that I mentioned. We had access to 5 months of login within the enterprise network and the attributes of the users, computers, and destinations. So in that sense, or data, we have a real data. For detection of the attack, we have used two different approaches. The first approach was that we started the system to work, and and um, and as it generates some alerts, we gave a subset of those alerts to security analysts to investigate those logins manually and say that how many of those logins are malicious in their opinion. So we gave 80 login out of 600 login, which was generated in a day, to security analysts. And it turned out that 13% of those login were labeled as somehow abnormal or malicious login within the network. But using this evaluation, we wouldn't know how many of the attack cases we are missing. As a result, we did a second evaluation in which we generated some synthetic attack traces which we basically knew what is the label of them. And we considered that all the login that happen within the network are benign login, all other login are benign, and then again ran the algorithm. So our algorithm was able to detect 82% of these bad logins, and it generates 0.3% false positive, in which if you want to get the actual number, it's about 600 alerts. And as you can see, a small number of them belong to the attack cases. That is the shortcoming of our paper. I will discuss in the next slide and provide more details about why this happens and what can be a solution. So as you can imagine, there is an interaction between the different measures of performance of the algorithm with different thresholds for the patterns that are generated by the system. And as you can see, there are points in this rock curve in which they show a good performance, and that was the point that we adjusted the setting of the system and we reported the performance of the system. In the paper, we have a detailed section of different aspects of our algorithm and our system and potential shortcoming and questions about this system. One of them was a discussion about evasion techniques that, well, of course, if an attacker knows and be able to move only over the existing edges of the login, then we wouldn't be able to detect the attack. That is true. But at the same time, we have to consider that the attacker might not satisfy all these conditions. Because imagine that if the attacker compromised the first machine and he steals some credentials of the admin, he doesn't have any way of using any other machine to log in. So basically, he cannot move over the existing edges. Of course, as he advances in the attack and captures more and more machines, he has more flexibility to move over the existing edges and evade detection. The other consideration of this research is a question of a poisoning attack because we use a history of logins in the past and then we mine or basically a structure of the logins within the network based on those logins. So if an attacker start doing some very small number of login that our system cannot detect, he might be able to add some patterns to the system which he can then later use to do malicious logins. To overcome this challenge, we will not include all the logins in the past. We have a threshold of saying that if, for example, a login has happened at least in 10% of the days in the history of the login, then we will include those login in the input of the pattern mining algorithm. And then as a result, either the attacker has to log in at least 10 days in the history, meaning more frequently, which increases the risk of the attacker being detected. But at the same time, there are cases that still the attacker will be able to poison. Um, and the other concern is transferability and generalization. Basically, our system doesn't have transferability, so you have to learn the pattern as you deploy the system in other companies because any of them has different configuration. And our system uh, basically only works in the network which have structures for small companies or networks which are not structured that well. Basically, there is no structure that we can mine to be able to do the detection. Okay, by saying that, in this work, we basically studied lateral movement based on stolen credential, which create new edges on the graph. We had somehow a reasonable result, but we are working on the improvement of the precision of the system in the next steps of the project. Thank you very much.
Hi. I don't know if I misheard the results, but so you took 5 months worth of data, and then you looked at it and you gave some subset of this to the analysts, and they found 13%.
Right.
Did you review that data to see what whether you had anomalies in it sort of programmatically, and then compare that to how the analysts did it? Did I misunderstand that?
I mean, the output of our system was a number of alerts, like 600.
Okay.
And we randomly chose a subset, which was 80, and we gave it to 3 different security analysts. And we relied on their label to say that as a ground truth,
Okay.
to say that if
So
that.
the output, the 600 were thought to be questionable, and then 13% were then confirmed with a label.
Sorry again?
Sorry, the 600 you output were questionable, I guess. They were flagged, and then you got the analyst to confirm, which
Yes,
gave you 15%.
exactly.
Okay.
Exactly.
Thank you
Yeah,
very
and
much.
that was all the alerts that the system generated.
I have one question. Oh, you can go ahead first.
Uh-huh. Yes, there are similarities. Yeah. Yeah. I mean, yeah, in this work, we didn't do such a study, but the general difference between access control mechanisms and here um, is that, like in a normal network, there are 50 to 90% over privileges because of the prediction of the disaster recovery and corner cases of login. So that is the reality that happens in the network. But as you said, I guess we have to do a comparison with automatic. Yeah, is a good suggestion.
My question is still about the numbers. So you have 0.3% false positive, right?
Yes,
So is that calculated against the 600 questionable numbers or against the total number of logins?
a total number of logins. Yeah,
Okay,
which
so
is about 177,000 unique combination of source, destination, and edges.
okay.
Yeah.
Do you have like false negatives
We don't know, but
numbers?
we did basically here by doing a synthetic attack traces. It seems like 20%. We missed 20% cases of attack
Uh,
because we don't have the real ground truth. We relied on the labeling of the security analysts
yeah,
for
yeah.
evaluation of precision. But to evaluate how many of the login we missed, basically we
Mhm.
created 20
Yeah,
uh,
yeah.
a number of synthetic attacks, and then we could capture 82% of those attack logins.
Okay. Thank you.